will be the recording also a mirror image of
Yeah, it should be okay. Wait. I also should do this now. So it records this screen. I hope it's okay. Dal jsem pin na tu hlavní, na tohle, ne? Na tu kameru, aby, protože ono to rovnou rekorduje tu kameru, ještě.
Když dáš na tu kameru, takhle je to na tu kameru, mám pocit, a když necháš tak, jak to je, tak rekordovat toho mluví. To je jedno.
Jednou to bylo divný, že jsme tam měli s Radkem. Takhle to mělo být pohodě. Yeah, okay.
Okay, so the point of this talk is to introduce the Hamilton-Jacobi equation in some good way that could serve well with some intuition about it and so on. Because if we read any textbook on classical mechanics, we get some sort of dumbed-down approach to this equation, which can be formulated in a couple of steps, really. First of all, we do some kind of magical canonical transformation with Hamiltonian. Then we need to introduce some magical thing, which is called the complete integral of the resulting partial differential equation. And no one really cares or attempts to explain what that complete integral even is. And then we say, oh, we don't really care about the complete integral because we have the separation of variables. And the final step of such an exposition is usually to work out the harmonic oscillator or something just as trivial. And then we call it a day and we don't return to the matter anymore.
Right. And Darek, you should probably also say that the complete integral gets people to believe that this is a full solution, which is not true. Complete integral is some solution, any parameter solution.
Yeah, we will get to that. We will get
it's confusing. I mean, the language itself is confusing.
Yeah, but
because it's not a complete solution.
Well, in some sense, it is, as we will see.
Yeah.
But let's keep it for it. And it's quite a shame because there is a nice physical intuition behind this equation, which gets completely obscured by such an approach. And I can also show a nice geometrical way of solving the first order PDE, such as the Hamilton-Jacobi equation, that will explain what the complete integral is and why do we care about it, and how do we use it to get solutions for pretty much any initial conditions we would want. But in some sense, the complete integral truly is what we need for the Hamilton-Jacobi method. And we will also see why. So let me start by doing some introduction that will try to connect the mechanics to optics. As you know, there are, in some sense, two kinds of optics. There is the simple geometrical optics, and then the wave optics, of course. And the geometrical optics is just a special case of the wave optics. When we take the wavelengths and send them in a limit to zero. And as we will see, the Hamilton-Jacobi equation is in some sense similar way of making classical mechanics work inside quantum mechanics. So now let's try to make that more precise. Of course, when we have geometrical optics, there is the Fermat principle. So we have the variation principle that looks something like this. We take this integral that just goes over some kind of curve. We essentially calculate the optical path over that curve, and then we demand that the variation of the optical path, the total optical path over the curve, is zero. And the trajectories that can do this equation are the correct trajectories of geometrical.
So n is the reference limit.
I'm sorry?
L is the refractive.
Yeah, that's the refracting force. And on the other hand, we have the wave optics, and that's pretty much governed by the wave equation, which can be written, for instance, in some way like this. If I write it in a four formalism with four vectors. So now there is a third kind of equation called the aconal equation that can be obtained from this wave equation when we go to the limit with wavelength to the zero. So how do we do it? First of all, let's just substitute something like this for this function u. And that u can be pretty much anything. For instance, in optics, these can be the components of the electrical intensity and magnetic induction. So we substitute a wave of such a form, and now just let's do the derivatives. So I will just do the first one first. So let's do it with respect to dsk with k upwards, and we get something. Now this is kind of a boring computation, but it won't be very long. So now we need to do the chain rule, so we get I over lambda d psi over dxk. And now we need to do another derivative too. So in fact, we take the derivative of k and we do this.
So lambda is a characteristic length scale?
Yeah. Lambda is just the wavelength that we will be setting to zero. Now we give this vector. So we once again get I over lambda I k. In this case, there doesn't really matter. Now we need to do the same this term, so we have I over lambda. Now let's do A. Now we need to hit the exponential, which will once again put an I over lambda, so we have 1 minus 1 over lambda squared. Finally, we need to hit the derivative once again. And all of this needs to be zero because it needs to satisfy the original wave equation. Now, when we multiply the whole equation with lambda squared and set lambda to zero, essentially the only thing that will survive such a process is this term, because only this term has 1 over lambda squared. All the others will get lambda to the first power or the second power, and when we send it to zero, then the rest of the term vanish.
And so what's the point? I mean, if you multiply it by lambda to the first, then you will have more terms surviving. If you don't multiply it, you'll have.
No, but well, they will blow up. They will blow up.
For instance, this one will blow up to infinity. right?
So you're doing like the minimum amount so that nothing goes up.
Yeah.
Okay.
And of course, if I would multiply it with lambda to the third power, then obviously everything would vanish. So that would make no sense. So after doing this, only this one term survives. And furthermore, the a and the exponential can now be safely cancelled because there is a zero on the other side. So we get a very simple equation which looks like this. This is, it has a weird name, it's called an A-common equation. And in some sense, as we have seen, it reproduces the geometrical optics inside the wave optics. So this psi, when we look at how we use the sign of substitution, essentially we can see that it is actually the optical length, because when we divide it by the wavelength, then we of course get the phase, and that's just how the optical path works. So this is an equation that describes geometrical optics using the optical length, but it's some sort of a phase, really, which is kind of weird because the geometrical optics doesn't know anything about phase, but here it is. We have such a wave description for geometrical.
I will not agree completely with this because geometrical optics is not the same as ray tracing. So in ray tracing, you have just some lines and you don't see the phase. But geometrical optics is rather what you said before, that it's some kind of special case of the wave optics. So in fact, there is some phase, even though it's
yeah, but it's kind, yeah, it's kind of weird because it blows up infinitely fast. Right. Anyway, this is how it goes with the optics, and we have kind of analogous situation in mechanics because there is classical mechanics, and of course there's quantum mechanics, which is some sort of wavy classical mechanics, if you permit me say this. So,
yeah, it's the WKB.
yeah.
Basically.
Maybe one more note to this equation. I think just saying that if lambda goes to 0, then we can neglect the terms that contain lambda. It's a little bit tricky because what it turns out is that this that is one side. Okay, so yeah. All right. So maybe another note that you can go one step further and look also at the terms that do contain the lambda after that multiplication, and then there are some real part and imaginary part, and that enables you to get some equation for the A. So to tell what the amplitude is as the wave propagates, which is often very useful.
Yeah, thank you. I just didn't want to go into too much.
You took the link lambda going to 0, but you can look at it as an expression.
I will keep this free here for the moment. What do we have in the classical case, classical mechanics? Essentially, we have exactly such a variation of principle in classical mechanics as well, at least when the energy is observed. It's the Mopperton principle, and it looks something like this, where the S0 is the thing that is called the abbreviated action, and we will shortly get to what exactly it is, but I'm sure you all know. Anyway. And of course, the quantum mechanics has its Schrödinger equation, so that is something like I bar psi E equals, and let's keep it simple and write it just for one particle in one dimension. In the X representation, then we get and now we can perform exactly the same kind of. And in order to make the calculation a little, let's say, a little nicer, a little less complicated in quotes, I will just say that psi now is e to the power of I s over h bar, where s is something, and I don't really know yet what something this is, but it will shortly turn out that it's no coincidence that I denoted it by S because it's exactly because it's correlation. But we don't know it yet, and just do such a substitution. And in fact, if we would permit this S to be complex, then we would get the amplitude here as well. So in fact, we can leave it out. Just to simplify it a bit. So let's just take this and plug into the equation, and we get I bar. Now we get another I over a bar, and there is Vs T.
I mean, there might, if you leave it out, there might be some problem with the order of each bar, because the A in front, that will correspond to what we would say first order in action. So there will be a term proportional where action is proportional to H bar.
Yeah, that's true.
Yeah. If you think of action as an expansion in H bar, then everything.
Yeah, I think Darek will probably also separate the real and imaginary parts, and then it will separate.
But
sure, but still the order of each bar is different for this.
But the thing is that I am doing it to the zero order essentially. So
sure.
We can
afford this is a one loop thing. So
I just didn't want to make this very long, which is something I'm already failing. So let's go.
I'm helping you failing.
So here, let's be wondering first that we just here. I go to H bar dx d and what is exponential b times the exponential. And now we can just go through this H bar, and I squared it, of course, to -1. What do we get here? So I over H bar is just a constant, and we outside. And here we can either take the derivative to get the second derivative, or we can hit the exponential to get another I over H bar and another first derivative. Oh, of course, here I forgot to include the exponential. It should be here as well. So if I write it like this, the exponential once more cancels. And now we can do exactly the same reasoning again.
You forgot the potential.
Oh, absolutely. Plus b well. So in this equation, the only thing that has H bar to first power is this second derivative. All the other terms don't have the h bar at all. So when we set h bar to 0, we get, and we write it some place here, minus bs over e equals. Now, this has an h bar in the first power, so when we set h bar to 0, it's valid. Here we have I over I, and the h bar will transfer. I squared is of course -1, so we get plus the first derivative squared and the voltage. So now we see that the analog of this Acon equation for optics is this kind of equation.
I think there should be a mass.
Oh, I'm sorry, 1 over 2. Here. And this equation is, of course, exactly the Hamilton-Jacobi equation. So this is actually the meaning of the equation, because the Hamilton-Jacobi essentially reconstructs the classical mechanics within the quantum mechanics. And now, what kind of thing is this act? I've already somehow mentioned that it will be exactly the classical action, but how can I see it? There are, of course, two methods. One is sort of hand waving, which I'm going to perform now. Essentially, when we did the same thing with the wave optics and geometrical optics, the side that was in this Acon equation was exactly the optical path. So when we have carried out the analogous procedure, we can sort of expect that this thing will be the action that is in this variation principle for the classical mechanics. And of course, now there is kind of a problem because this doesn't have any time dependence. But I'm just going to hand wave it out, and I will proceed to the normal and regular derivation of this. So I just wanted to point out this kind of correspondence that quite strongly hints at the fact that this should be the classical action.
Is it not already because we already because that's the Hamilton-Jacobi equation? So
yeah.
So its solution is something whose interpretation is the classical action.
Yeah, that's true. I just mean we don't know it yet.
Oh.
I just want to proceed in some logical fashion.
Yeah, that basically you're missing is that P is ds dx.
Yeah, and of course they will turn out shortly that it's exactly the case. So this is some sort of an introduction, and now, of course, it would be quite weird if we couldn't deduce the Hamilton-Jacobi equation from the classical equations. If we needed the quantum theory to sort of get it out of that, but some limit. And of course, there is a way to derive the Hamilton-Jacobi equation completely classically, and I will show that. And by that, we will also see that this really is the classical action. And of course, this argument is something that you have probably seen a million times, but for reference, I'm still going to go through it. Just to keep the talk logical, and I know that there will be perhaps 8 views on YouTube, but still, if anyone looks at this, I would like it to have some logical coherence. So now let's just one out. keep the Hamilton-Jacobi equation here, and we can proceed to the classical mechanics. Of course, we know that we have the action principle that looks like this. And by the integral, I mean that we have picked points, fixed them, and then the equations of motion are obtained by varying the path between the two points. And I can, of course, do the normal derivation of the equation of motion by just performing this variation and then doing the integration by parts. So I will very, very quickly show how it's done, because there will be a point where we need kind of expression for the variation. So if I vary this, I can essentially write this as the xk, where x are coordinates, plus dl over dx dot k t. Now, what I know is that I can switch around the variation with the time derivative, so essentially I can write this like that. And now I will perform the usual integration by parts, which essentially means that I'm going to add the time derivative of this term times this without the time. So these two terms, in fact, now form complete derivative with respect to time, and we can write it. Of course, I have to get rid of the so this is, in fact, such a time derivative. So, since the integral is with respect to time, we can just cancel sort of the integration and the derivative, and we get that this kind of quantity is just being taken as the two endpoints of the integral, let's say a and b, and then there's the rest of the integral, which can be written as here's a minus, because we have a minus here from the expression. KB. And so now the usual argument is that we keep the endpoints fixed and we just vary the path between them. So here on the both endpoints, this variation needs to be zero. So normally we would just let it vanish. And then of course, this bracket needs to be zero for this to work, for this integral to be equal to zero. And this way we get the equations of motion. But now let's flip it on its head, sort of. And let's consider a situation where we have one point that is fixed. And now let's kind of shoot trajectories out of that one point into various other endpoints like this. And every time we shoot such a trajectory, we only take into our consideration a trajectory that is allowed according to the equations of motion. So if we do it this way, then suddenly these equations of motion are always satisfied. So the integral just vanishes automatically. And when we take the action of such a path just as a function of the endpoint, then I get that the variation of the action is equal to this. And now here's the endpoint and the starting point, and we kept the starting point fixed. And we just shoot the trajectories from one fixed point, so the variation is 0 in that point. And essentially what remains is the variation of the endpoint goal. So I get this very simple relationship for the variation of the action, and from this I can see that if I take the action as a function of the coordinates of the endpoint, I can just write down this equality, because this is some sort of differential. And now we can use the fact that, of course, this kind of derivative is exactly the canonical momentum. And we get the very well-known fact that the derivative of the action with respect to a coordinate gives us the corresponding momentum.
Right. I think you mentioned it, but I think there's some problems with how we set up the variation principle where usually when the here the action principle there, the initial and final time are kept fixed.
Yeah.
But here, effectively, it's not fixed. I mean, it changes with.
Well, the time can still be fixed, right?
I'm not so sure. Because
you can issue the particles with various initial velocities. Right?
Yeah, but what the criteria is now that x is the same, but time you might need other different times to perform the part.
No, but you say that you start at a given point at time example 0.
Yes.
Whatever.
So the initial time you can keep it.
Yeah. Yes.
So I'm worried about the final. I'm worried about the final.
So there's no options. You can either keep it fixed or you can also vary.
Yeah.
But it's talking about the case when it's fixed. And
Yeah,
the case when you vary is also interesting because from that you will get
I'm going to do it.
Yeah. Okay. Good. Okay. So the energy is then different.
Yeah.
Now. Yeah,
No.
but not later. But not later. Later, when you go to the Morpheus principle, it will be the other way around. Okay, good.
Of course, well, you essentially talk about what I just wanted to say, because this thing holds if we keep the times in the endpoint constant, and if we allow the variations in time as well, then of course the action will be a function of that end time too. And now we need to have a look on what it is going to be. And for that, we can once more use the variation principle. Only now I'm just going to rewrite it using the Hamilton. We of course know that if we sum these kind of products and subtract the Lagrangian, we get a Hamiltonian. That's just the definition. So I can trivially rearrange this to express the Lagrangian. Okay, minus Hamilton. And of course, I can exert this expression right here. Starting to get a less critical out. Get rid of this. And continue. And of course, this x dot is just dsk over dt, so we can write it in such a form. pk dxk minus hg. And now, if we allow the variation of the endpoint, the variation of time at the endpoint, we can pretty easily figure out what the derivative ds with respect to dt is. Because we already know that these pk's needs to be that with the derivatives with respect to the coordinate.
Okay, I guess here to be precise, we are actually still in the Lagrange formalism.
Yeah.
So the Hamiltonian is not really the Hamiltonian, but it's the energy function.
Yeah. Yeah, it's still.
Of course, we have the same value as the Hamiltonian, but it's
Yeah,
not.
it's still a function of
Yeah.
position and velocity.
Yeah.
No.
And the same with momentum. Momentum are not independent variables. Momentum depends on x and x dot.
Now, well, maybe I made this slightly, but perhaps we should do it like this. Instead of rewriting it like this, I will do something a bit different. This means that we always have this relationship. We differentiate with respect to time. And now, another means the time that will be at the next one. This will be a slightly better way of doing it because now we can insert what we know already from the case of fixed endpoint coordinates that will just give even better. We can just do. Sorry, I use. What I mean is that we can write this derivative in another way, just by considering that the s is some function of time coordinates. And now we just use the here we get the k over v. Of course, this is just x k with the dot.
Right. So S is the on-shell action now.
Yeah, it's still the initial action. Right. And by comparing these two and using the fact that this derivative is exactly the momentum, by comparing this, we just get that the time derivative is minus the momentum. And this is a bit tricky because we need to kind of take care about what action it really is and what we are varying, so I'm a bit confused with it. So the expressions are very important to us because now we can just take the very trivial, the very trivial expression that the Hamiltonian is just the Hamiltonian as a function of coordinates, momenta, and time. And now when we know that the momenta can be expressed like such derivatives, and the Hamiltonian itself is also a derivative of the action, then we can just put it into this relation. So we get that the Hamiltonian is in fact the time derivative, and now we have I think if you look at this, it exactly coincides with this equation. Because if we take the Hamiltonian for one particle in one dimension, which is E squared over 2m plus b, this is some function of the coordinate, and we replace the p with the derivative with respect to the coordinate and the Hamiltonian with the time derivative, we get exactly this equation that we obtained by doing the limit in the quantum. So this truly is the Hamilton-Jacobi equation once again, and by this we have effectively shown that this weird S that we use in the procedure of quantum mechanics really was the classical action. So the action, in some sense, serves as the optical path for the classical mechanics, which is kind of a nice thing to know, because otherwise it's kind of hard to imagine what it would actually be. It's some kind of weird thing that we actually don't know exactly, and we just try to very it's hard to put some geometrical or physical meaning on it. And this is the meaning. So that's at least one nice thing about this procedure.
Yeah, and there is also that meaning is even deeper, because you can imagine that all the trajectories go from the initial point to the final point, and then the deployed waves along them, and the deployed waves have exactly the wavelength given by the momentum. So it's quite the same situation as in Fermat principle, where in order for the light to propagate on some trajectory, all these nearby trajectories have to interfere constructively with it, so it's the same here.
And essentially the point is that if we send the h bar to 0, then the oscillation of the wave will be very violent. So it really takes only very, very small displacement, and the two nearby parts cancel completely. So essentially that's the quantum mechanical meaning of this classical action principle. We need that the action stays at least for some little amount of space around it, but then stays the same, so that these violent oscillations will just cancel. And so this is how we obtain the classical equation, I mean the Hamilton-Jacobi equation by classical means. And now we can actually show how to work with this equation and how to put it to some use, because this thing actually makes people feel weird. At least I have a weird feeling about this equation, because in some sense we have, for instance, the Hamilton equations of motion, which are just a nice system of ODEs, first order ODEs, and now we just replace them with PDE, which is much more complicated, much harder to solve, and somehow we say that this is better. And how come? How is that even possible? And I will try to show it by doing the canonical transformation that you are probably waiting for. And I will grab the notebook so I don't miss anything. And I'm sure you all know how this canonical transformation works, but I will spend a minute just deriving how they should look like. Essentially, we have this action principle. So if we have some positions of omega and Hamiltonian, we could transform it into some other set of new positions, omega and Hamiltonian, that I will just denote by such a twigger. And now, if we demand that these new position momenta Hamiltonian describe the same system as the old things describe, then of course it's natural to demand that the action doesn't change in quotes. But by doesn't change, I actually mean that it can only change up to a complete derivative of some function. Because here is the time integral of something. So if we just add a complete derivative to the Lagrangian or to whatever is under this integral, then of course, when we take the derivative, it just spits out a constant in front of the integral. And then if we vary the path and look at the action, of course, the constant is not going to change it. So we need to have that the old action principle, okay, and the new one need to generate the same motion. And so these two things under the integral can differ only by a complete time. So essentially, if I write it in this form, then the difference of the two things must be, T must be completely differential. And this F is, of course, called the generating function of the transformation. There are four possible kinds, according to what kind of position or momentum is under the differential here, but we don't really care about that. We just look at the time dependence. And since this is to be this differential of some function, then looking at what if at the dt, we get that the df over dt needs to be the new Hamiltonian minus the old one. So,
So Darek, at this point, I guess you have to say that you, for instance, the scaling, you would not consider scaling of the new.
yeah. I mean, this is the usual treatment, but still going to kind of go quickly. Maybe more than before. If we have such kind of relationship, now there is an interesting thing to note. We have this, that the time derivative of the action is minus the Hamiltonian. And here we get that if we use some function f as the generating function, the new Hamiltonian will be the old one plus the time derivative. So what if we use the action as the generating function? Of course, we get that the new Hamiltonian is the old one, and then the derivative of the action with respect to time, but that's of course exactly minus the old Hamiltonian. So the new Hamiltonian will be exactly zero. So this is another reason why this is so nice, and exactly I would have to say the only reason. Because now when we do such a canonical transformation and get a zero Hamiltonian, then the Hamilton equation of motions, equations of motion, I'm sorry, are so trivial. They are just the positions are constant and the moments are constant. Because their derivatives are. So in this way, we can see that the Hamilton-Jacobi equation is some kind of conservation law machine, or I don't know how to call it, because it can generate conservation laws for us. If we can do such a transformation, it exactly spits out these momenta that will be critical. So this is why we actually care about the Hamilton-Jacobi equation at all, because it can give conservation. And of course, if the Hamilton-Jacobi equation fully separates, which I'm not going to describe in more detail yet, then we could do the solution by the Hamilton method or whatever. But even in the case when it doesn't fully separate, or when we find only some less dimensional familiar solutions than we need, then we can obtain a lesser number of conservation laws, but still we get at least some conservation laws. And this is the value of the Hamilton-Jacobi equation as I see it, because in the Lagrangian or Hamiltonian formalisms, you can get conservation laws, but there are some preset procedures of how to look for them. Like the canonical momentum is conserved when the corresponding coordinate is silent, and otherwise it is not conserved. And the generalized energy is conserved if the Lagrangian doesn't depend on time. And we have such nice rules, but they fail or they can give us less conservation that we want or need. And this procedure will give us, if we carry it through up to the end, will give us just the full amount of them.
Yeah.
How do you use what I do think so? All right. How sorry, I maybe a few sentences. Oh, maybe how do you give us the laws?
Well, if I do the transformation, then in the new coordinates I have this.
Oh, that's right.
Then the new coordinates need to be specified, but the generalized momenta that will come out of this are something that we didn't insert into. We didn't know that before.
Right. But of course, there's no free lunch, and it's the problem is it's very difficult to find a solution.
Yeah, of course.
Hamilton-Jacobi equation. If it was simple, then of course, I mean, in principle, the other could also generate 2n conservation laws. Namely, if you are able to solve your system completely, not very likely, but if you could, then you can take the 2n initial conditions and rewrite them in terms of the dynamical variables, and then you will have your conservation. But of course, that will be very difficult in practice.
I'm not so sure about that because I think somehow, I'm not completely sure. I think that these constants that you get are in fact somehow the initial conditions. So
well,
not really the topic is sponsored.
You have 2n of these equations, and the generalized coordinates are something that we have to put in.
Yeah.
These are the initial conditions, the integration constants.
And then
the other momenta, they will fall out of that, and they will give the conservation laws.
Right, and you have the canonical transformation, so you know how the dynamical variables are in the new dynamical variables.
I should perhaps add something that I was going to say later, but we get interrupted. That this function, the generating function, is currently a function of the old coordinates, the new coordinates, and the time. So if I'm going to use the action as such a generating function, then it needs to be function of these things. And of course, it already is a function of time and the coordinates, but what are going to be those new coordinates? This is something that we don't yet know. And
I think it's the initial conditions at some time. At some
initial
time, at the time.
In some sense, that's true, but this is the way that leads to the thing called the complete integral, because we need this S as a function not only of time and coordinates, but some other n values that will serve as the new coordinates. And now the question is, where are we going to get this space? And fortunately, quotes, we have the solution of some differential equations. So such a thing is a huge number of solutions. So there is a huge amount of freedom, and we should be able to get some constants or parameters like this. And that leads to the notion of the complete integral, at least somehow intuitively. Yeah.
And so you're guaranteed that your conservation will also be independent because it's just like a canonical transformation that you cannot get like dependent coordinates from independent coordinates.
Yeah.
Okay.
And you really need X simply, you don't need, usually it's P simply there.
I think it doesn't matter, right? Because if I
conventionally,
I think I have seen both.
yeah.
It doesn't matter, I think, because that differs only by
Sure.
data transformation.
Sure.
We actually don't care very much about like whether this is the new coordinates or the new coordinates. So if we need n new parameters in this S, then it's of course natural to search for a solution of this Hamilton-Jacobi equation that would have such a form that depends on n parameters. And generally, such a solution of any partial differential equations is called a complete integral. So that's why we want to get the complete integral, because it will just contain the correct amount of parameters so that we can proceed to the canonical transformation and get our conserved quantities, which will be the new moment.
So when you say that the complete solution, complete integral also in some senses, the full solution, you don't really mean that it's just the solution you want.
I'm sorry, can you explain?
So, yeah, so I made a statement that the complete integral is, strictly speaking, not what you might expect from the name, a full solution to the equation, to Hamilton-Jacobi equation. It is an n-parameter, non-determinate n-parameter solution.
But the thing is, and that's what I will want to show in the rest of the talk, that this is actually sufficient.
It's sufficient, but it's not the full solution.
Yeah, but I mean, it's if I have any.
I just want to stress this point, but yeah, what we need for physics application, and but mathematically it's not the total solution.
Well, maybe let me proceed and we will see what I want to say. So now we have shown how the complete integral gets into all of this, and why we are even interested in searching for it. And in the rest of the talk, let's do some crash course on PDEs and show where does it come.
You know, if you just once why the complete integral is so good, because I missed that sentence before. Sorry for that.
Yeah. In order to do the canonical transformation, we need the generated function to be a function of time, the old coordinates, and the new coordinates. And the action, of course, is already a function of time, the old coordinates. But we don't really know what the new coordinates should really be. And the point is to search for such kind of solution to this Hamilton-Jacobi equation that would depend on n parameters that we could then use as the new coordinates. Because in some sense, we need the action to depend on n more things and we need to get them somewhere. And the complete integral is just such a solution that contains the requirement.
Yeah, there will be integration constants from
Yeah. I know that this is perhaps not fully convincing. I haven't found a better way to show that. No, one more. Now let's do the crash course of PDEs, because the complete integral is something that is useful in solution of any kind of first order PDE. It's not something that would be connected to the Hamilton-Jacobi equation itself. So we can sort of build up a general theory of solving such equations, and it really would be a crash course because there's not so much time left. But still, I hope to show what's the meaning of it, complete integral, and why does it get the name complete.
No, I don't think you have to hurry. I guess if it takes more time, maybe you can support for more time.
Oh, of course, I can. But so let's start by just totally forgetting all the physics for now, and let's write down the first order partial differential in any kind of form. And I will use, let's say, that as the independent function that we are looking for, and I will use such a notation that the derivative with respect to x is called p, and the derivative with respect to y is called sorry. And I will just restrict to 2 dimensions, just to make it simple and just to limit the amount of writing I will need to do.
And for us, physicists, should we think of x and y as x and t, or t and x, or if you want to play the game?
If you have any partial differential equation, then the x and y are just the independent coordinates.
Oh, okay. So it could be
in our case, it would be one coordinate, but we can do it. Okay, so just grab any kind of first order PDE that would have such a sub-function of the coordinates, the function that we are looking for, and the first derivative. And now we have a look at the geometrical meaning of this equation. Of course, since we have only 2 coordinates and one unknown function, then we can visualize the function z that we are trying to solve for as some kind of a graph introduced. So we would have x and y as coordinates in R3 and z, of course, and then the solution z could be thought of as some kind of surface in this R3. And that will also explain why I chose only 2 coordinates, because in 3D space we can still visualize. And it's at least possible to draw some picture. Anyway, if we just look at one point of such a surface, then the equation says something about what the coordinates and the derivatives need to satisfy. And the derivatives actually show what the normal to this surface is going to be. And why is that? That's very simple, because if I fix x, y, and z, then this is just some relationship between P and Q. And on the other hand, if this is a function of x and y and draws surface, then we know that the gradient of 3 just serves as two components of the normal vector. If -1 in the z component, we get the normal in 3D space. That's because if I rewrite the solution in this form, just as f minus d equals 0, and then do the gradient, then of course I get the -1. And we know that the gradient is exactly in the direction of the normal. So it's P and Q actually said what the direction of the normal should be. But the equation kind of leaves a lot of space, a lot of freedom for choosing these P vectors. Because even if we fix one point on the surface and fix the x, y, and z, then still this is one equation for two variables, P and Q. So essentially there is a whole one-parameter family of possible normal directions at each point, so that the surface still satisfies the PDE that we are solving. And if we have a look at how it goes, and we kind of try to visualize, let's say that this is the normal vector, and I have a little kind of surface perpendicular to it, then as the vector moves, the surface will kind of describe some cone. And why is a cone? Because the surfaces are emerging from the same point. This is the point that we are looking at on the surface. And when we vary the normal, then the surface, then the little kind of little surface we are making perpendicular to the normal that describes a cone, because all of those little squares or whatever are touching the same point. So, well, I can't draw it properly, but in fact, what we get is some kind of cone. It doesn't need to be a circular cone, it just can have some sort of a wide shape, but it is a cone.
The normal form of the cone, or the surface itself, or normal.
Both of them. But I mean the surface. If we just grab a point, and now we want to know in which direction the integral surface, so by integral surface, I mean the surface d equals the solution, in what, then I get this family of allowed directions of the integral surface. Because the normals wiggle around, and as I turn the allowed directions perpendicular to the normal, then it will describe exactly such a cone. It can be kind of difficult to visualize, but
So it's you have a one parameter family of planes that we default. So you do something like this.
yeah.
But yeah, I see that it can be like, for example, if you have some clay and piece of something hard, and then you do that, then what remains from the clay can look like a cone, but otherwise I don't see the cone there so much, because
Yeah, it doesn't need to be really a cone as a circle.
sure.
It can be.
But even then, I just don't need many plane.
Yeah, well, to make it exact, all the little planes for a family of possible directions of the surface. So the surface needs to be tangent to one of those planes. And we can form something that is called the envelope of these planes. And that is the surface that shares the tangents with every one of those planes.
Yeah, that's what I meant by the plane.
Yeah.
You do this and then it remains.
So effectively, and exactly said, the envelope of these little planes is going to be that cone.
Okay, fair enough.
And the enveloping process is okay because we just care about the tangency of the surface to the cone. And if the envelope is something that shares the tangent to each of those planes at some point, then of course the tangency goes strength through. So if it is tangent to the cone, to the surface, and the cone is tangent to some of those allowed directions, allowed planes, then of course the surface is still tangent to one of those allowed planes, and we are okay. So it's good remove.
So if you took F to be something special?
Oh, do you mean this? I'm sorry. This is something entirely different than this.
Right.
I meant this just as a way to write the graph of the function, nothing more.
Right.
And to explain why that -1 occurs in this component.
Okay, yeah, but so when you get the cone, is that because you have imposed the PDE?
Yeah.
This is basically just a visual representation of private manifolds in general.
Yeah, and are you assuming something about the form of the PDE?
Not really. The cone may be degenerate in some sense. For instance, all of those planes can turn about one line, so the cone will be.
So it's just an arbitrary. The function is more or less arbitrary.
Yeah, otherwise, this is more or less arbitrary. We just demand that it's sufficiently differentiable for us to do what we want to do. But otherwise, we don't really impose it.
If the cone, you mean a two-dimensional object in 3D?
Yeah. This is just a visualization, as Sandra said. Because if we want to build a geometrical theory of this with some nice intuition, then of course it's nicer to visualize the PDE, which gives some condition on what the surfaces have to look like. Then it's just nicer to have a visual representation of the PDE. And that is that at each point we have such a cone, and the solution.
And what does the different points in the cone represent?
Oh, you can imagine it as a very little cone. It just
So the first of all, the tip of the cone corresponds to the point we are looking at.
It's just some kind of helping device to help imagine the tangents.
I think it's like if you have, for example, you know what's the direction of some, you have some vector field, and then you are looking for the integral curves that.
Yeah, that's a good analogy.
So you somehow move a little bit on one and then on the next one. So here you will somehow move along those poles. And
if you have a normal vector field, then you can integrate it, and the curve is going to fit the vectors such that it is tangent to all of them.
right.
And here, the cone is just a similar device. We have a cone in each point, a little cone, and we are trying to fit a surface that will touch the cones at each point. And if we get such a surface, then we can be sure that it is the solution of the PDE that we are searching for. Because touching the cone is exactly described by this PDE. But anyway,
For the first order, we can think of the normal vector as constant, and this is the surface.
absolutely. So if I have such an equation, then these two things, the derivatives, point in the direction of the norm.
Right.
And there are only some allowed directions, because they still need to satisfy this. And I just, instead of saying that the resulting surface needs to be perpendicular to some of those normals, I just say that it needs to be tangent to that cone. But it's just a visualization, right? You shouldn't be looking too much into it. But it helps to show what it is really about.
You can also think about it like a four-dimensional subspace in 5 dimensions, which is you have 5 total independent coordinates x, y, z, p, and q. And you solve the equation, it gives you some four-dimensional surface. But now we also need to solve that p is the derivative of z with respect to x, and q is the derivative of z with respect to y, which sort of gives you this. You can think of it as a surface and then points on the surface. So your four-dimensional substrate will be like a direct product of the z function and then the derivatives on this function.
How do you get that equation that n is gradient minus 1? What does it mean?
Well, let's imagine that I have any kind of such a surface that is described by z equals some function 4. Then I can rewrite this as such an equation, g minus 30. And now I know that if I have an implicitly defined surface in 3D or distance, this would be a two-dimensional surface in 3D. Then if I do the gradient of this function, I will get the norm. So I do the gradient, I will say x derivative, y derivative, because the g is function of x and y. And there is the z with the minus. So this derivative is minus. Okay, so we spend a quarter of an hour looking at the code. Just for future reference, this construction is called the motion. Okay. So now, when we have this kind of visualization, we can sort of proceed to solve the equation stuff. And there's one other device that we are going to use. Essentially, if we have some kind of surface that will solve this equation, then we can try to draw a bigger surface here. Something like that. No. This. Then here in each point of the surface, I have those cones. So there's cone like this, and like this, and like this, and so on. And these cones are touching the surface along some lines. So if I draw the lines along which the cones are touching the surface, I will something like this. point. And such a curve is called the characteristic. And now what I'm going to do is this. I'm going to just make a very little ribbon out of the surface. Just look tiny amount to the left and to the right. And by the tiny amount, I mean just such a little amount that the information about the normal is preserved. Really, what I'm trying to say is that I'm going to take the points along with the normals. At each point, I need to know the normal. And when I take such a collection of the points and the corresponding normals, it can be visualized as a very, very little ribbon of the surface because the normals give some direction to the surface. Then we get something that we could call a characteristic strip, because it's a very, very tiny strip with some kind of direction. And the nice thing about these strips is that we can find them just by solving some kind of ODE system without reference to the solution. So these characteristic strips could be used to actually solve the PDE. And how does it work? Let me just start at some point that lies on the solution surface. And now I'm actually able, and I will do that shortly, to write a system of ODE that will be able, that will just draw the strip out of the initial condition. It will allow us to continue and make the strip. So when I'm able to do this, I'm in fact able to do a solution to some initial problem for that particular PDE. And that's because the initial problem, which has some form of parametric curve in the 3D space, essentially I just have a curve and I demand that the values of the function that I'm solving for have some particular values at each of those points. So that forms a curve in 3D. And now if I set a curve, I'm actually able, if I just use the PDE and some sort of little trick to actually make a strip out of that, and that's possible. We'll show how. Then once we have this, we can use the system of ODEs that I will show shortly to shoot out a characteristic strip out of each of those points. So I will be able to start here and draw one little strip that will be a characteristic strip, so it will be tangent with the points. And still I can go from the next point and draw another strip. And in this way, I could go from each point of the initial condition and shoot out a characteristic strip. And all of those strips together would form some surface that would give us the solution. And of course, this procedure can break down in various ways, but just let's don't take that into consideration now, and let's focus on the general case. And it's 2:30.
In this initial curve, somehow, I think it cannot be arbitrary because it also has to somehow be aligned along with codes.
Yeah. But not all initial conditions will be valid for the PDE. But still, you have those cones, and there you have only one curve, and those cones are two-dimensional objects. So you have a lot of freedom of fitting these little kinds of planes around that initial condition, which is one curve, to fit the cones, if we can see what I mean.
But when I shoot from one element on that curve, as you, if I do that shooting, is it unique or is there some freedom?
It's unique, provided that the initial condition isn't chosen badly. By badly, I mean the cone.
Okay.
The cone needs to point sort of sideways. If I had a bad initial condition, that would just run along those cones. Then, of course, I couldn't shoot the straight along the cone and make any sense of it.
I don't see how there can be so much freedom in that solution, because the initial condition is somehow
There is no freedom.
the solution of that differential equation depends on some arbitrary functions.
Yeah, but once you set the initial condition, the solution is unique.
Okay, but yeah.
Well, that's the general solution, of course, depends on the function. But when you just use the initial condition, then the function will have to take some particular form so that it fits the initial conditions. So, in fact, if you have the general solution, you still have to put something concrete in place of the function in order to fit the initial conditions. So now I've shown the idea of how to use the cones and the characteristic strips to solve the equation, and now let's just do it completely. And let's write down some equations for the characteristic strip as this thing is called. So, of course, if I have one point on the surface, and I draw another surface like this, and I make a tangent plane to this point, then I still can, this should be x, y, z, I can use some other three coordinates, let's say A, B, and C, in the solution. And of course, there will be one condition that will relate these three together, because it still has to be the tangent plane to that solution. So, in effect, it has to satisfy the differential equation. So, it's very easy to get the condition. Essentially, we can, instead of A, B, and C, we could write dx, dy, and dz, because these are some small steps away from the point where the tangent plane is touching the surface. And then we get a very simple differential condition, which is also we would expect for such a function, and we know that these derivatives are the p and the q. So we surely need to have this condition for the tangent plane. And of course, the p and the q still needs to satisfy the original equation. So we have before, p q still needs to be equal to 0. So now we essentially can use one of those coordinates p and q as derivatives as a parameter, because this will make some relationship between those two, so we could use one that as a parameter to express the other one. So now let's say that we want to use the p as a parameter, and the q will be just a function And after doing that, we can just go and differentiate this with respect to the p. And the dz, dx, and dy are just the coordinates in the tangent plane. So when we differentiate them with respect to the p, they will just vanish. So in fact, here we just have the p, so that differentiates to 1, and the q is some function of p. So this is a useful relation that if we rearrange a little bit, will give that dq over dt equals minus dx over dy. Just by putting the dx on the other side of dividing by dy. So this can be useful. And now we can differentiate this original equation with respect to p, because we still parameter, and we keep the x, y, and z fixed, because we are still looking at one point and at the tangent plane at the point. So, in fact, differentiating with respect to x, y, and z will give zeros, and we will get df with respect to dp times the derivative of p with respect to p, which is 1, plus df dq, and here we get the derivative of dq over dp. And that still needs to be equal to 0 because we have a 0 here. So now we can rearrange things a little bit, because the dq over dp is actually the same thing as minus dx over dt. So we can use that. Bye. And now we can just multiply by dy and get df over dt dy minus df over q dx equals 0. And that is already one part of those equations that we will need for the characteristics tree, because I can write it in another form. This, I can write this as dx over df dp equals dy over df dq, and that should be equal to some parameter dt. And why this works? If we look at this one equation, then of course we see that the dy needs to be some multiple of this derivative, and dx needs to be some multiple of this derivative. Of course, that multiple doesn't need to be 1, but when I just get that multiplicative constant or whatever, and I call it dp, then I can rewrite these equations in such a form. And this gives a couple of parametric equations for the characteristics tree, because this f is just the PDE that we started with. So we can differentiate it with respect to P or Q without any problem, because we know how the equation works, right? And what we need to do still is to add the other 3 things to this system. So we need to get the dependence of Z and of P and Q on this parameter. Now we just need to do it. Of course, the dependence of Z is not really hard to do because we already have this. So now if we let's write it in such a way where we have times dx over dt plus q over y over t. Then we already can plug in from this equation because dx over dt is exactly this derivative. So instead of this, I can write this derivative df over dt. Similarly, I can write df over dq instead of this derivative y with respect to t. So in the end, I have that this dv over dt is p times df dt plus q times df dt. So that's the third equation, because now I just could rearrange it to the same form as these two equations, just by multiplying by dt and dividing by the whole right side. We would get third equation we put in here. So we wait for it, and we have dz over the whole right side. So that it's e df over e plus q df over d. And I'm aware that this is a bit boring, but we will need these equations so that yeah, of course, it's leaving, so when I derive them, I will probably call it today and return to the complete integral next week. So still the p and the q dependencies are missing, and we need to get there somewhere. But it's not that hard to get them because we can still use our PDE. And now let's differentiate it with respect to x and with respect to y. So first, let's do it with respect to x. So, and here, b is the function of x and y. So are these two. Because of course the normals vary from both. I will switch. And which first, right, is more clearly. Okay. So if I differentiate with respect to x, then I get df dx, and the derivative of x with respect to x is of course y. The y is totally independent of that, and then we have df with respect to dz, and then we need to put dz in x. And we do the similar thing with the other two coordinates. And we are still zero on the right side. Oh, and I'm doing total nonsense because I said I was going to differentiate. No, I'm not going to nonsense. Partial differential time. And we can get absolutely analogous thing for the y. So still we get df over dy equal b. And now we can start to plug things that we already know into these two equations. So first of all, these derivatives are P and Q respectively, so they're ceasing. And now, of course, the P and the Q are also sub-functions of the parameter T, because we have the characteristic script that is function of one parameter T. And of course, the normal direction needs to be function of the parameter as well. So here we can actually say that dp equals, and still we are using just the old chain law. Boring, but useful. And now there is a little bit of a trick. Recall that we are using the name P for such a derivative and Q for this derivative all the way along. So actually, if we differentiate P with respect to Y, then we get the second derivative with respect to X and Y. And that, of course, needs to be the same as the second derivative done in the opposite part. So we get this relationship between the P and Q. So what I now want to do is essentially to match this expression with these two weird terms. And how do I do that? First of all, dx over dt is something that we already know. It's df over dt. So I can exert that over dt. The same thing holds for the dy over dt. That's the key derivative of f. Okay, and now we can use the trick that I mentioned, because if we look at this, what we want to replace, then I have df dp dp dx. That's here, that's okay. But here we have dp dy df dq. And instead of dp dy, we would like to have a dq dx. But as we have shown, these derivatives are deterministic. So in fact, these two terms that I've outlined here are equal to dp dt. So this completes this kind of boring derivation finally. I can get that dp dt is just minus the rest of the terms here. And if you look at them, then we have just derivatives of the f, which is a function that we know because it's the partial differential equation we started with, and here's the p, which is also okay. So we have that it's minus df x plus df d dx, which is okay. And I won't do the same thing for the other equation, but you can probably believe me that we get E equals minus df dy plus df z times Q. Once again, I can just rearrange it to this form and trying to put this in here to get dp over minus x plus p df z, that equals to minus dq over df dy q df z. And this equation that's sticking over the whole board is a system of ODEs that truly determines the characteristics. And the equations are called the Lagrange equations. And they are precisely useful because they allow us to solve the PDE. So now, since this is just a system of 5 ODEs in 5 independent, in 5 functions that we need to solve, we can just use the usual existence theorems and so on to get the thing that we are looking for, which is that as long as we use a good initial condition that actually satisfies the equation, then we can proceed to shoot out the characteristics tree. This will allow us to continue from that point. And in this way, we can proceed with the solution because we can grab the initial condition and shoot from each point. And apart from some cases where the initial condition is in some way bad, for instance, as I have drawn, the curve that would be this through all the cones. Of course, then if we are shooting along the cone, then we would like the cone to point sideways in some sense to get started. So if we just do it, we get a whole lot of these characteristic strips, one from each point of the initial condition, and together they make up the integers. And that's also easy. So that's how we can solve the initial problem for this first order PDE. And I think I will call it a day and stop here because well, it's left. So and he was so interested in the complete integral, so I will keep that for the other day. So thank you so much. Of course, if you ask something, you can, perhaps I will be able to answer. Maybe.
Yes, so I just wanted to your previous point about Hamilton-Jacobi and the canonical transformation and the conservation law. So if I get some Lagrangian, then the way to go to the conservation laws is to write down the Hamilton-Jacobi equation, to solve it in such a way that you get n parameter solution there, and you use that as a generic function to solve the canonical transformation, and you get the conservation laws.
Essentially, that means that once you solve the Hamilton-Jacobi equation and you get the n parameter family, then you can just differentiate with respect to those n parameters, and each of those derivatives will be the new momentum, which is constant, and so is the new conservation law.
Yeah, but of course, if you start with Lagrangian, then just the system it describes doesn't have to have two conserved quantities, right? So I guess the abstraction would be that you cannot get an n parameter solution of the Hamilton-Jacobi equation.
Yeah, I guess if the equation will be in some sense degenerate, then these procedures will break down, right? There are some edge cases and corner cases in which this can fail. And of course, I'm not really going into them because it would be a matter for a whole semester of PDEs and one or two talks.
But can it still partially work that you get only like a half parameter solution of the Hamilton-Jacobi, you get some conservation?
For each constant, then for each dimension of the family, you get one conservation. Because if you write it down in such a way that you have that the S is equal to something you know and that contains a few of those constants, plus some unknown function, which is the method of the other things that you haven't really determined yet, then you can still differentiate with respect to those constants that you already solved for, that you already established. And still you are going to get some conservation loss from that.
Thanks.
And now I guess that this is the true value of the Hamilton-Jacobi process. Because if it fully separates, or if it can be solved fully in this sense, so that we have the n-parameter familiar solutions, then most of the time, it just means that if you use the same kind of coordinates, the same kind of formulation, then your Hamiltonian or Lagrangian formalism will just give this. So in those cases, the Hamilton-Jacobi doesn't offer anything really new, at least when it comes to the solution. But still, there are other uses for the Hamilton-Jacobi equation that I will outline in the next talk, which are more theoretical, but you can, for instance, get the adiabatic invariance from it, or the echelon variables, and so on. And those things are dependent on the Hamilton-Jacobi formulation.
Okay. There is some other questions? Running out of time. Yeah, thank you very much for the talk. What do you want to do?